Okay, so now we are on to our second case of our improper bridge. So we are dealing with the second picture there. Let C be a crossing where B terminates and C overpasses. So that would be right here, this crossing here. Let U be then the loop from C to C. So we're talking about that loop right there. So one can see that with a Reidemeister 2 move, we would be able to move this black string out of there. So we would end up with something like this as our new projection. So this is our P of L, and then our P prime of L would be the second projection. If the Reidemeister moves reduce the number of crossings, then K, you can see, would be reduced equally. So in this case, it reduced it by 2 crossings. These 2 crossings were eliminated. And you can see that the bridge number was also reduced by 2. Our bridge that was a 2 length is now only a 0 length. So it was reduced in the same amount as the number of crossings. If that's the case, we could see that the number of crossings in P prime of L minus the bridge number in our second one, in our second projection, would therefore be equal to the original number of crossings minus the bridge number. Okay? And that, of course, does fit our theorem or our lemma. If the Reidemeister move were not to reduce n, so how could that happen? Well, we could just have this, and that would fit our definition excuse me, of an improper bridge, because it just says it's an open segment and one or both of the crossings at which B terminates also has B over crossing. So it doesn't say we have to have any particular bridge length. So there may not be any other crossings in that loop. If that is the case, then a Reidemeister 1 move would undo that loop, and this would that projection would then cause it to just be a single strip. Okay, maybe more accurate drawing after the Reidemeister 1 move might be something more like that. Since the Reidemeister 1 move eliminates exactly 1 crossing, then we can say if this is our new projection right here, then the bridge length or bridge number has to be less than or equal to the original projection's bridge length minus 1. Which, Dr. Wiley, I would like to kind of talk about why this would be less than, but in my head I'm not really sure that I understand why it would be less than and not just strictly equal. Like, I obviously understand it's reducing it by 1 crossing, but why wouldn't it be exactly equal? Clarification on that would be good. Please and thank you. So then, therefore, we again have that the projection or the number of crossings in the P prime projection minus the bridge number has to be less than or equal to the number of crossings in the original projection minus 1 minus the bridge number minus 1. And then that would be, and I needed to write this moved over more. And that would be equal to the number of projections in the original projection minus the bridge number in the original projection. So that all fits our lemma again. Okay, so now we will go on to our third picture, or our third improper bridge definition. On this one, We can let C be the crossing where B terminates. So that would be here, this crossing. And a Reidemeister 2 move, R2, is going to move this string out from underneath that. So our new projection, that would be moved. We would still have this circle here being interrupted right there. Okay, at that point, because we had this, the curve being not a closed curve, it is an open curve, but it's kind of ending at itself. Because that's the case, it's going to continue to be that way, but we've removed any other crossings that could be moved. So that's only going to leave you the one crossing that has to go under here. Since something came into that circle, something has to come out. So if that's the case, your bridge number is now exactly 1. We eliminate every other undercrossing except for that one. And so N and K get reduced equally again. And that would simply be because whatever undercrossing you're taking off would have contributed to the bridge number, but it's also contributing to the crossing number, so both of those reduce equally. And if that's the case, as we've had before, it fits our lemma. And so thus we have proved our lemma. It works for all of our different improper bridge types. A few more definitions we'll need. P, your projection is crossing free if the number of crossings in your projection is 0. That should make sense. If there are no crossings, it's crossing free. The projection is alternating if the length of the bridge is 1 for all bridges. Alternating basically means you go over, under, over, under, over, under. So you're never going to have 2 overpassings in a row. You're never going to have 2 underpassings in a row. And of course, it would be non-alternating if the length of the bridge is greater than 1 for at least one bridge, because that would then mean you have 2 overcrossings or 2 undercrossings in a row. Your projection is composite if there's a simple closed curve C which intersects your projection transversely in 2 points, and both the interiors of C and the exterior of C contain crossings. So the simple way that I have been thinking of this with the help of Dr. Wiley, if you can circle a portion of the knot and intersect it in exactly 2 places. So if you have any type of projection, but somewhere in that projection you have something like this, where you can circle it, it's only intersecting 2 spots, and you have crossings within it and outside of it, then it's composite. It would be prime if it's not composite. A prime link can have a composite projection if one factor is a non-trivial projection of the unknot. So what's the unknot? The unknot is just, of course, again, our single loop, but that would be a trivial projection of it. We are talking about if it has a non-trivial projection. So if we add maybe a Reidemeister 1 in there, if we're bending or looping it or adding any crossing in it, and of course you could do that, multiple times, and it would still be the unknot. So if it has a composite projection, then it is a composite projection. Did I just double say that? If it has a composite projection, then it becomes a prime link, would become composite. Any projection containing a trivial loop, therefore, then is composite. There is one exception, a particular projection of the unknot, and it's actually that second one I drew, this one here, would be an exception, and that is because if you go to draw your circle, here's my circle, this does not fit the composite definition because it says it has to have crossings inside and outside of C, and in this one it only has it inside. Now our article says this is the only projection that does that, and this confused me because I thought about, okay, so say we had something like this. Like technically that is a different projection and it also fails to fit this, but he's actually thinking of that, I suppose, as the same thing, although it's not. So because it is the only connected projection with the crossing number 1, it forms a little bit of a basis for some of what he does moving forward. Okay, so Kidwell's main result, theorem 1. Let the projection of L be a regular length projection with n crossing points. Let K be the maximal length of any bridge in our projection. Then he's saying the degree is less than or equal to n minus k. What we are going to do is we're going to prove, we want to show that there are no projections that violate this theorem. So we want to assume we do have a counterexample. So suppose our projection, our P of L, is a counterexample. Suppose it has the smallest possible number of crossings, and we'll still go with this the maximal length of any bridge. Okay, so assume we have a counterexample. It has a maximal length of any of the bridge, and we also are dealing with the smallest possible number of crossings. So then, because it's a counterexample, we would be saying that the degree of Q of L must be greater than n minus k. And then what we're going to do is we're going to prove that there is no such example. So let B be our bridge of maximal length. If B is improper, then we know by lemma 0, which we've already proved, that there exists a projection, P prime of L, where the number of crossings in that projection minus the bridge number in that projection is less than or equal to the number of crossings in the original projection minus the bridge number in that projection, which would just be equal to n minus k, simpler version of this. And we know that n minus k, based on our counterexample assumption, would have to be less than the degree of Q of L. Also by lemma 0, which I didn't mention this, but if you look back at lemma 0, we proved this part of it, this bottom line. We proved the bottom statement with our 3 different improper bridges, but I didn't really mention this, but it's actually kind of visually obvious that the number of crossings in our P prime projection has to be less than the number of crossings, because by Reidemeister moves, the original number of crossings is reduced in each example that I showed you. So kind of a visual proof there. So also by lemma 0 then, here we would know that, as I just said, the number of crossings in the P prime projection has to be less than the number of crossings in the original projection. But then that means right here, our original n, our number of crossings, is not the smallest possible number, which was one of our things that we assumed here at the very beginning in order to get to this. So that is, of course, a contradiction. And so we don't have a valid counterexample there. Okay. All right. Now, let's let our bridge length, maybe we should let it be 0. So we know it can't be improper. We've already decided that. Now let's see if we could end up with a bridge length of 0. Maybe that will be a counterexample. Well, if that's the case, that means the projection of the link, if your number of crossings is 0, the only thing that your projection could be is that, the trivial projection of the unlink. Well, if that's the case, then our number of crossings is obviously 0. And then the degree of Q has to also be 0. But then again, if we're looking here, our degree of Q is 0, and we wanted it to be greater than n minus k, but n minus k is also 0, so we do not have that it is greater. So again, we do not end up with a valid counterexample. So since we know that B cannot be improper, then it can't be a closed loop, because any closed loop is going to be an improper bridge. Therefore, it has to be an open segment, because that's all we have. We have closed links, closed loops, and we have open segments. So we've ruled out closed loops, so we're looking at an open segment. But because we know it's not improper, we also know that the open segment can't run into itself. It can't be that situation where one of the terminating spots terminates into itself. Okay, so we can't have that situation. So that means we have to have an open segment that isn't running into itself. So we might have something like here, add some crossings. Okay, and we would be saying that this part of it here would be our bridge. So let's perform the crossing change from our skein relation using this part here, C right there, as our site. So this original projection we would say is projection L, but of course that would also be our L plus. So our L minus is going to take this and change this undercrossing into an overcrossing. So now our bridge would look like this. So this crossing is changing here. That would be our L minus. And for our L naught, our bridge would do this. So that crossing now bends up here. And for our L infinity, oops, we do the same way, but same thing, but bend the other way. Okay, so we can see that these two crossings, they have a bridge length of K or more. Okay, so we've already, if our original bridge length was K, we still have all of those crossings. We still have each of those going over, so our bridge length would be at least K, but it's certainly possible that we could have more crossings coming off of here, so it could be more than K. Or same thing here, there could be more crossings happening over here, so it could be greater than K. The crossing number, our N, has to be N minus 1. Because we have one less crossing in these two projections than we did in our original projection. So therefore, the degree of Q of L naught has to be less than or equal to N minus 1 minus K. And likewise, the degree of Q of L infinity has to be less than or equal to N minus 1 minus K. Okay. Now let's suppose that ax to the m is some non-zero term of q sub L, which would be the same as q of L plus. Okay, and that would be where m is greater than n minus k. Well, by our skein relation, our second rule for our q polynomial, the x to the m term of q of L minus must then be negative a of x to the m. In order to cancel, because ax to the m minus ax to the m is going to cancel. And why would they have to cancel? Because the q polynomial of L naught projection and the q polynomial of the L infinity projection can't have a degree of m. Okay, they can't have any term with a degree of m because m is greater than n minus k. And of course, these two projections have to have one less crossing than the other two. So even multiplying by x, it's not going to work. Okay, but also keep in mind that your L minus projection has a bridge length of at least k plus 1. Okay, and that is, of course, because you are adding an overcrossing when you switch that. So this undercrossing becomes an overcrossing, so your bridge length is at least, I don't know why that is so thick, at least k plus 1, because of course you could have other undercrossings after that, but we are only looking at that one particular site, so it's k or more. So Q of L naught has a bridge length of at least k plus 1. Then the degree of Q of L naught, therefore, has to be greater than or equal to m. M is greater than or equal, or I'm sorry, just greater than n minus k, which is greater than n minus k plus 1. But then what does that tell us? K is not the longest possible bridge anymore, because P of L, your projection of your L minus projection has a bridge that is longer. So again, we end up with a contradiction, and therefore there are no projections. We've gone through all of the options. There's no projections that will violate the theorem. There are no counterexamples, and so we are proved. We have our theorem 1 proved. Dr. Wiley, I'm looking at the time, and I'm thinking maybe I should stop there, because I think I'm about 45 minutes when that's all together, and including that one prop that I wanted to use, explaining that. I could go into theorem 2. If I don't do theorem 2, then I would eliminate this discussion here and this discussion here, because those things only deal with theorem 2. And if I were to do that, it would cut down a few minutes, but I think I could, like, as I've gone through, I think there's some things that I skipped that I would want to go back and explain differently. That would still, I think, take me to the time. If not, if you do want me to do theorem 2, my only concern is theorem 2, the very end of it relies on a separate lemma. So like, I feel like that's going to add way too much time. So maybe I could just say, show the other lemma and just take it without proving it, and then just go through the theorem. I guess that would be an option. Tell me what you think about that. And then I'll record here my theorem 2, what I would say, assuming we are just taking that second lemma, the lemma in the appendix, as fact without going through the proof, because I definitely don't think I would have time to go through the proof as well. Okay, but let me say then what I would say about theorem 2. Hopefully this is all making sense. Okay, so Kidwell also adds a second result of theorem 2, which says that if a projection is prime connected alternating with n crossing points, then the coefficient of x to the n minus 1 in the Q polynomial of L is a positive number. Okay, this theorem, or proof, the theorem is true for the lemniscate projection, and we know that because the lemniscate projection is, of course, prime. We've already discussed that. It's connected, and it is alternating because we are over, under, only one time there, with n crossing points. Okay, and in this case, our n happens to equal just 1. There's only one crossing. The reason we know this is true is because our first rule is that the Q polynomial of the unknot, which this is, because remember a Q polynomial is an invariant, so it doesn't matter what projection we're dealing with, it has to equal 1. Okay, so the x to the n minus 1 in this case would be x to the 1 minus 1, x to the 0, which means we're dealing with no x at all. So of course, this fits. Whoops, excuse me. Okay, so now let us suppose, that's our base case, now let us suppose that the theorem is true for any projection with less than n crossings, so that we can then prove it that it is possible or true with exactly n crossings. Let's C be any crossing in our projection. Oops. I'm not going to write that out actually. That's silly. Let C be any crossing in our projection, and then we will perform the operations of the skein relation. So our first projection is just our this is our L projection, which is our L positive projection. Our L naught projection, I'm going to write these out. I'll have these out on the screen first. Okay, so our L naught or our L minus projection still has n crossings, and it has a bridge number of 3, and that is from right here, 1, 2, and 3. By theorem 1, which we just proved, we know that the degree of our Q polynomial of the L minus projection has to be less than or equal to n minus k, which we know would be equal to n minus 3, since our k is 3. By the skein relation, the coefficient of x to the n minus 1 in our Q of L projection must equal the sum of the coefficients in the x to the n minus 2 in Q of L naught and Q of L infinity, because you're going to multiply it by another x from our skein relation, so that would give you the n minus 1s. So those must be equal. Since L naught and L infinity are alternating projections, which again I will have that drawn out. I'll have all 4 of these drawn out prior, so they're there. Because they're alternating projections and have n minus 1 crossings, because we delete a crossing on that, then the proof ends up getting completed by induction if at least one of our projections, if either P of L naught or P of L infinity is prime and connected. And that's the lemma that we would have already taken here. And so we have a proof again, and we are good to go. Okay, and then I have my references, the main article by Mark Kidwell, other resources I used, and I need to still put these ones into the right format. So that's it, and then I would be ready for questions. I already am seeing things that I want to do slightly different, like if we do decide to do theorem 2, then I would move the vocabulary, this slide and this slide, after theorem 1. So I would do theorem 1, then do these, and then do theorem 2. But let me know if you think I should do theorem 2 or cut that stuff out. And in my head, it's based on time, but open to any and all suggestions you have. I'll be happy and willing to fix or make better anything that I can. I look forward to hearing what you have to say. Thank you. Oh, and one more thing I noticed on the video, the background is all blue, and I know it's like kind of a little bit blurry, the video. It won't look like that. It's just the recording is doing that, but when it's live, it should not look like that at all. The background is much clearer. It's just a basic blue, and everything should be just more precise, more clear.